All right, now we've already mentioned that invertibility has something to do with injective and surjective. And in this theorem, we make it formal that a linear transformation is invertible if and only if t is both injective and surjective. So the picture again is you have two vector spaces here. Every point in here goes to a single point here. All the points in V are hit by points in U. So if I take the inverse, I basically just reverse all of the arrows. And if I don't have a surjective linear transformation, I can't reverse the arrows. And if I don't have an injective linear transformation, I can't reverse the arrows because there are two arrows pointing to one place here. All right, so let's get down and take a look at the proof. So t is invertible if and only if t is injective and surjective. So let's assume we have to go two ways. We have to show invertible implies injective and surjective, and we have to show vice versa. Injective and surjective implies invertible. So the first way is actually a little bit easier. If t is, let's assume t is invertible. So we need to show that t of x equals t of y implies x equals y. Okay. So let's assume this. We're going to start out with x. X is the identity operating on x. That's the definition of identity. Let's write identity as t inverse composed t. Right? And let's reassociate that t inverse composed t acting on x is t inverse of t of x, but we have the assumption that t of x is equal to t of y. So I can replace t of x with t of y. Then I unpeel and go backwards, and I find out that t inverse of t of y is just equal to y. Right, so I started out with x. Using the fact that t of x equal t of y, I moved over to the t space, I made the identification, I went back to y, and I showed that x, in fact, has to be equal to y. Okay. Now, to check that t is surjective, okay, I suppose that v is in V. Now, if it's invertible, then t inverse of V exists and is a vector in U. Okay. Now, so this is a vector in U. Now, consider t of this vector in U. I can call this U. T of this vector U is t composed t inverse of V. That's equal to the identity operating on V, which is just the vector V. So what have we done? We've shown that for any vector in V, I can find a vector in U, namely t inverse of V, that maps to that vector V. Okay? So in fact, we've shown that t is surjective. All right, so as I said, that's more the easier way. Now remember, we're trying to show that a function, a linear transformation is invertible if and only if it's both injective and surjective. So now we have to go the other way. Let's assume that t is both injective and surjective. Then we can create a function, s, using the fact that it's injective and surjective, and show that t is invertible. Now this is the same way you do it with functions, not just linear transformations, but let's go through this proof. To this end, we choose any v in the vector space V. So remember, are we going from U to V or V to U? Let's take a look here. We're going from U to V. So in order to define the inverse, we want to define a function from V to U. All right, so in order to define a function from V to U, we have to define a function for any arbitrary vector V in V. So choose an arbitrary vector in V and V. And since t is surjective, there must be some vector since t is surjective, t is in the range. That means that the preimage is non-empty. There must be some vector u that maps to V. There must be some u in t inverse of V. That means that t of u is equal to V. Okay. Now we already know that since the inverse image of V is non-empty, it always has this form. T inverse of V is equal to U plus Z. Z is in the kernel of T. That means that T of Z is equal to 0. However, since T is injective, that means that the kernel is trivial, that K of T is equal to 0. So that means that Z must be equal to 0. There's no other possibility. Okay, so there's a unique u in T inverse of v. So I can define this linear transformation S, which is going to turn out to be the inverse of T, by S of v is equal to this unique vector u, which is in T inverse of v. Now notice that we've used both injective and surjective to define this function S. We used surjective to show that the codomain was equal to the range, so that the pre-image of any vector in the codomain is non-empty. So we were able to find some vector in the domain that maps to the codomain. On the other hand, because T is injective, we were able to show there's only one vector that maps to every vector in the codomain. So we've used injective and surjective to come up with a mapping that basically associates with each vector in the codomain a unique vector in the domain. Now all we have to do is show that this mapping is in fact an inverse of T. And we just need to verify those two equations. Starting with any vector in U, we need to show that S composed T of U is equal to U. So if you define V is equal to T of U, then T inverse of V must be equal to U, so that S of V equals U, and that gives us that S composed T of U is equal to U, which is the identity of U. On the other hand, if we start with V, there's a single vector U that's in the inverse image, and consider T of that set, okay? T of that unique element, okay? T of U is equal to V. So that gives us the other way. So in fact, when you take T composed S, you get the identity on V. All right. Okay. So here's the cartoon that in fact we have, for instance, 0 goes to 0V, and because it's injective, only 0U goes to 0V, nothing else goes to 0V. Same with U2. U2 goes to V2 since U2 is the only vector that goes to V2. I can define a reverse arrow that goes uniquely to U2. These slices actually consist of a single vector. All of these inverse images are single vectors. So I can define a well-defined function backwards. So injective and surjective is called bijective or invertible. And bijective is the same as invertible. All right, now, suppose you have a linear transformation like this, and you want to compute the inverse. Now, the inverse is going to act on polynomials, because T takes matrices to polynomials. The inverse will take polynomials back to matrices. Okay. Notice that the domain is not all 2 by 2 matrices. It's simply the symmetric 2 by 2 matrices. All right, so I'm looking for a function that goes from polynomials back to matrices that inverts this function. Well, if I can find a function that works on a basis of polynomials, and here's a basis of polynomials here, if I can define a function on this basis, by the linear property, I can find a function for any polynomial that works. Okay, so let's consider T inverse for these three basis vectors. Now, how does this work? Well, here we have, if we want to find the matrix that maps to 1, we have to solve three equations. We have to solve a plus b plus c equal 1, because this coefficient should be 1. I have minus a plus 2c is equal to 0. And I have 2a plus 3b plus 6c is equal to 0 as well. Okay, so I have three equations in the three unknowns, a, b, and c. I can write this up as a matrix equation. And here it is right here. Okay. When you row reduce this, you get minus 6 10 minus 3, that means that C equals minus 3, B equals 10, and A equals minus 6. Okay? So we've simply plugged the A, B, and C into the matrix form. Okay? So this gives us T inverse of 1. If we want T inverse of X, it's going to be very similar. In this case, you want the first coefficient, A plus B plus C, to be equal to 0. So I have a very similar setup here, similar set of linear equations, only the constant vector changes. So instead of wanting 1 plus 0x squared, I want 0 plus 1x plus 0x squared. Same coefficient matrix, same way to row reduce. You get minus 3, 4, minus 1. Okay. Do the same thing for x squared, you get a similar result. Okay. Now I want you to notice something, that if we had taken this coefficient matrix 1, 1, 1, minus 1, 0, 2, 2, 3, 6. Now the first constant vector was 1, 0, 0. Second constant vector was 0, 1, 0. Third constant vector, 0, 0, 1. Okay? Okay. Now we've seen this extended form before. And we know that if we row reduce this matrix and we get identity over here, then the matrix that we'll get on the right-hand side is the inverse matrix. Okay? So that's a preview of what we're going to see, is that in fact the matrix for the inverse linear transformation is simply the inverse matrix for the original linear transformation. Okay, so instead of doing 3 separate row reductions, I could have done all 3 row reductions at once, and we know that when we do that, we'll get the inverse of the original matrix that was on the left-hand side. Okay, so I'm going to skip down here. We have this theorem about composition of invertible linear transformations, that if you have 2 invertible linear transformations, then their composition will also be invertible. Okay. And you can actually work out the inverse, that the inverse of the composition of 2 invertible linear transformations is the composition of the inverses in reverse order. Now you may have seen that in regular functions, that the inverse of fg is g inverse f inverse. It's the same sort of thing. It's the very same proof. You can prove that this function t inverse s inverse works as the inverse for s composed t on the right and on the left. You have to try it on the right and on the left to show that it is in fact the inverse. All right, so let's stop here for this one.